Okay, we're starting now with electrostatics. We're going to take a little bit of a break from mechanics and look at electrons instead of, big things that are moving. So electrostatics, let's start by defining what it is. Electrostatics or electrostatic equilibrium is a condition when charges are at rest. So think if you've ever been shocked, that's because you had two charges that were at rest and then they had a little spark when they combined. What is charge? It's an inherent property of electrons and protons. This should not be anything new in terms of what charge is. The only way you get it is by having an electron and a proton. The symbol for charge is a Q. You might see a lowercase q, you might also see an uppercase Q. Either one, they mean the same thing. So the symbol for charge is Q. You'll probably see me using them interchangeably. The lowercase or the uppercase does not matter. The unit for charge is a coulomb. C-O-U-L-O-M-B. And the symbol for a coulomb is a capital C. So unit for charge is Q, either capital or lowercase. Unit for charge is coulomb, capital C. This should be review. Protons are positive. They're positive if they have an excess of protons. Electrons are negative. Objects are negative when they have an excess of electrons. If you have an equal number of protons and electrons, then the object is considered neutral because positive and negative cancel each other out. I hope that is review. It should also be review that like charges repel and opposite charges attract. Okay, so coulomb is the unit for charge, and the fundamental charge is the charge of an electron. 1.6 times 10 to the negative 19th coulombs. You don't need to memorize that, and we don't really use it that often. It's just a good number to know. It is on your formula sheet, so again, nothing to worry about memorizing, and we use it very rarely in equations. Okay, the law of conservation of charge. Just like energy, charge cannot be created or destroyed. So if you have a positive charge that's appearing somewhere, you need a negative charge appearing somewhere else so that your net charge does not change. So what does that mean? If there's equal numbers of protons and electrons, it means the universe on a whole is neutral. So the universe isn't positive, the universe isn't negative, the universe is neutral. So conservation of charge, charge can move, but it can't be created or destroyed. Okay, so on that note, charge is moving is what allows something to be charged. So charging is the process of adding or removing charge from an object, usually going to occur through the movement of electrons. Think about it. A proton is what makes an element, or the number of protons is what makes an element. So you can't really remove protons from atoms because then it would change the kind of element it is. But what does move are those electrons from the electron cloud, or whatever they're calling it these days. So electrons can move from one atom to another, and that's what allows objects to get charged. There are three main methods of charging. The first one is friction. If you've ever taken a balloon, rubbed it against your hair, and then stuck it to a wall, that's charging by friction. You're rubbing two objects together, and by rubbing, the electrons are being transferred from one to another. The second type of charging is conduction, and that's when you have a conductor that's going to come in contact with another conductor, and the electrons just move. And I'll define what a conductor is in a minute. So think of a conductor, if you have two metal objects, one of them's charged, then it can easily pass electrons over to the other just by touching. The third method of charging is induction. So this is probably the most confusing one. With induction, you have a charged object brought near a neutral conductor. You have another neutral conductor touching the first conductor. The charged object is going to make electrons flow either into or out of. So this depends on whether the original charged object is positive or negative. So the electrons are going to either flow into or out of the first neutral conductor, and then the connection is broken and that neutral conductor stays charged. I know it sounds confusing, let's look at what's actually happening. Let me make this a little smaller so we can get everything. There we go. Okay, so step 1 of induction. You have 2 metal spheres, both neutral. You have the charged object, in this case it's positive, being brought near but not actually touching a neutral conductor. So the positive object here is attracting all of the electrons from the neutral conductor. You have a second neutral conductor already touching the first neutral conductor. All of the positive charges, let me rephrase. All of the electrons from this one are coming over here, so this is becoming positively charged. This second neutral conductor is now positive, brought away because the electrons went into here, and then this positive charge, which was never touching, is taken away. So the first sphere became negative here, and the second sphere became positive. So charging by induction, you are inducing a charge, and I guess we use the word inducing because you're not actually touching the object. What's going on there is what we're going to look at next. It's being polarized. So this positive charge here is attracting electrons in this neutral sphere. The second neutral sphere is having its protons and electrons being separated because this one is doing the same thing. So this is a negative side, positive side, negative side, positive side. These negative electrons are being attracted over to this sphere. So when this one's pulled away, it lost electrons. This one gained electrons from this sphere, meaning that this one is now negative and this one is now positive. I know this might be confusing. We'll try and actually do this in the lab tomorrow. Or I should say in the classroom, not a full lab, but we'll try and do this in the classroom to see how this actually works. Again, you can't actually see the electrons moving, but you can see the effect of inducing charges. Okay, conductor is a material through or along with charges move easily. The biggest example we have is metal. Usually wires are made out of metal because they can easily have electrons travel through them. Insulators are materials on or which charges remain immobile. So an example of that would be glass, plastic. Wood's usually a pretty good insulator as well. So insulators are going to be hard for charges to move through. Conductors are easy for charges to move through. And that's the reason why conductors are the only thing that can charge through induction. I'm sorry, not induction, conduction. Okay, the last thing we're going to look at is polarization. This is what's going on with induction. You have a slight separation of positive and negative charges in a neutral object when a charged object is brought near. So the neutral object as a whole is neutral, but it's going to have a positive side and a negative side. So here's an example. You have a soda can, it's neutral. You bring a negative object near the soda can, the electrons are repelled, so they're going to go to this side. The other side of the can is going to become positive because of the lack of electrons. So now, this is a neutral, polarized can of Coke. Again, neutral because equal amounts of protons and neutrons, but polarized because they're on opposite ends. And because those charges are separated, there is a force between them. So polarization force arises because of that slight separation in a neutral object, not because objects are oppositely charged. So in other words, you can have a force between a neutral object and a non-neutral object because of polarization. Polarization is always attractive between a charged object and a neutral one. And since one side of the neutral object is closer to the charged object, the force is greater, and that's going to allow a net force to exist. We're going to look at electric force next, and that's where this will become a little bit more relevant. But just know that you can have a net force with a neutral object because of polarization. I want to do 3 quick examples. And then we'll do a lot more of this in class. So first, we want to determine if the object is an insulator or a conductor, and then determine the net charge of the object on the right. So just by looking at this, here's the object before. You can see where all of the positive charges are, where all of the electrons are. And then after. Since all of these electrons moved, you know that this has to be a conductor. And also, here's the negative charges. Negatives have to be attracted to a positive object. So that means the net charge of the object on the right is positive, and the object on the left is a conductor. Okay, the next two are the same picture, but different scenarios. So first we have metal spheres 1 and 2, they're touching, both are initially neutral. The charged rod is brought near, so first this charged rod is brought near the spheres, not touching. The charged rod is then taken away and the spheres are separated. What is the charge now on each sphere? So let's just think about what's going on. When the charged rod is brought near, you have the object polarizing. So brought near, this side's becoming negative, this side's becoming positive, this side becomes negative, this side becomes positive. But then the rod's removed. So when this rod is removed, the charges are free to go back to where they were. So both objects are going to become neutral again, and then the spheres are separated. So what is the charge now on each sphere? They're both neutral. So Q1 is 0 and Q2 is 0. They weren't charged by induction because of the order that things happened. So again, the rod brought over to the first sphere polarized it, but because the rod was removed before the spheres were separated, nothing actually changed. Let's now look at the next scenario. Again, we're looking at the same picture. So both spheres are still initially neutral. We have the charged rod being brought near. The spheres are then separated before the rod is removed. So charged rod brought near is going to make this whole side negative. Again, positive, negative, positive. The spheres are going to be separated while the rod is still here. So that's going to make this a negative sphere. So Q1 will be negative. Q2 is going to have an excess of protons. So Q2 will be positive. So the scenario in number 3 was charging by induction. The scenario in number 2 was nothing. It was just polarization, but nothing was actually charged. Okay, so conceptually, if you're having trouble with this, hopefully it makes a little bit more sense once we see some of this in the classroom. But we'll do some practice with this and just trying to figure out, what's happening to the charges before we start putting any numbers or looking into the electric force.